Hello everyone, welcome you all in a video lecture series related to heat and mass transfer. We are dealing with convection heat transfer. Today we are going to learn about Reynolds analogy. So here we go related to Reynolds analogy. So this analogy is the interrelationship between fluid friction and Newton's law of viscosity. How we are going to see in an upcoming lecture. According to Newton's law of viscosity, the shear stress will be given as tau naught is equal to mu multiplied by du divided by dy, where tau naught is a shear stress, mu is nothing but dynamic viscosity, du is the change in velocity, and dy is the change in length in a vertical direction. So du divided by dy is nothing but change in velocity with respect to change in length. In a fluid, heat flow along a y direction, that is nothing but vertical direction, is given by Fourier's equation. And we know this Fourier's equation, that is nothing but q is equal to minus Ka multiplied by dt divided by dy, where k is the thermal conductivity, a is the area, dt is the change in temperature, and dy is nothing but change in length in a vertical direction. So this is nothing but heat transfer rate by conduction. Now we are going to consider that Prandtl number is equal to 1, and we know that Prandtl number can be interpreted as mu Cp divided by k. Here mu Cp divided by k is equal to 1. We can rearrange this equation as k divided by mu is equal to Cp, and also we can get this equation in the form of a thermal conductivity as k is equal to mu Cp, that is nothing but dynamic viscosity multiplied by specific heat. By using Newton's law of viscosity, we can write the dynamic viscosity as dynamic viscosity mu is equal to dy divided by du multiplied by tau naught. So if you put the value of k in a thermal conductivity equation, that is nothing but value of k is nothing but thermal conductivity value k is equal to mu Cp. In a heat transfer equation, q is equal to minus k multiplied by a multiplied by dt divided by dy, and instead of mu, if you put this value dy divided by du multiplied by tau naught, we'll get the heat transfer rate q is equal to minus Cp multiplied by a multiplied by tau naught multiplied by dt divided by du. Now here we have to integrate this equation with the limits. So for that purpose we have to separate out the differential term, that is nothing but du and dt. So du we are going to transfer to another side, and we are going to interpret. So while providing the limits, we should take care about the Prandtl number. Here the Prandtl number is equal to 1, that is nothing but velocity boundary layer is equal to the thermal boundary layer. So that is nothing but what? The velocity boundary layer line is collapsed with the thermal boundary layer line. So the thickness of thermal boundary layer at a given point is equal to the thickness of velocity boundary layer. So at the plate surface, we know that the viscous forces are more dominating. So the velocity of fluid layer in the vicinity of the surface equal to 0. And also this particular layer will attain the equilibrium with the surface, so that the temperature of the layer which is adjacent to the surface having temperature equal to the surface temperature. And in the same manner, at the outer edge of the boundary layer, the velocity we are getting equal to the free stream velocity or the mainstream velocity. And also, as we know that velocity boundary layer is collapsed with the thermal boundary layer, so temperature of the fluid layer will get equal to the mainstream temperature. Now here the integrated equation becomes q divided by Cp multiplied by a multiplied by tau naught, integration of velocity with the limits 0 to u, where this u is nothing but mainstream velocity. equal to minus of integration of temperature with the limits Ts to T naught, where the Ts is the surface temperature and T naught is the mainstream temperature. So integration of du will get as a u, and if you put the limit upper limit minus lower limit, we will get the u only. Here the integration of dt will be t, and if you put the upper limit and lower limit, t naught minus to will get. Now here the negative sign, if you take inside the bracket, then you will get ts minus t naught. So the equation becomes q divided by cp multiplied by a multiplied by tau naught multiplied by u is equal to ts minus t naught. So if you rearrange this particular terms, we'll get q divided by a multiplied by ts minus t naught is equal to tau naught multiplied by cp divided by u. Here we know that q divided by a multiplied by ts minus t naught is nothing but the local heat transfer coefficient, that is h suffix x. Now if you put up the value of q divided by a multiplied by ts minus t naught as h suffix x in the previous equation, we'll get the equation h suffix x is equal to cp multiplied by tau naught divided by u, where cp is the specific heat, tau naught is the shear stress, and u is the mainstream velocity. Now the tau naught, here we have to concentrate. The tau naught equation can be given as c suffix fx multiplied by 1/2 of rho multiplied by u square, where this c suffix fx is the local coefficient of drag or local skin friction coefficient, and rho is the density, u is the mainstream velocity. So after putting this value and rearranging the equation, above equation, we'll get the equation h suffix x, that is nothing but local heat transfer coefficient, divided by rho cp multiplied by u is equal to cfx, that is nothing but local coefficient of drag, divided by 2. Now here h suffix x divided by rho cp multiplied by u is called as Stanton number, or we can say that local Stanton number, because we are dealing with the local heat transfer coefficient. So this Stanton number will becomes a local Stanton number, and it is denoted by st suffix x, that is nothing but local Stanton number. So this local Stanton number relation with the Nusselt number, and Nusselt number having the relation with Nusselt number, Reynolds number, and the Prandtl number. So it represents the Nusselt number divided by product of Reynolds number and Prandtl numbers. So the Nusselt number, local Nusselt number, nu suffix x divided by local Reynolds number, re suffix x multiplied by Prandtl number is equal to Stanton number, local Stanton number. So is equal to cfx divided by 2. So this equation is called as Reynolds analogy. By using this interpretation, we can infer heat transfer data from the shear stress measurement. What this particular Stanton number signifies, the Stanton number is equal to h suffix x multiplied by delta t divided by rho cp u multiplied by delta t. So where this h suffix x delta t is nothing but actual heat flux of the fluid, where this rho cp multiplied by u delta t is nothing but heat flux capacity of the fluid flow. Further, in case of a laminar boundary layer, on the flat plate, we have the local Nusselt number is equal to local heat transfer coefficient h suffix x multiplied by desired location distance from the leading edge, that is nothing but x, divided by thermal conductivity. And we know the relation with the Reynolds number and Prandtl number for the laminar flow. So the Nusselt number in the form of a Reynolds number and Prandtl number can be interpreted as local Nusselt number is equal to 0.332 multiplied by local Reynolds number raised to 1 by 2 multiplied by Prandtl number raised to 1 by 3. Now here, dividing both sides of above equation by local Reynolds number multiplied by Prandtl number raised to 1 by 3, we will get the local Nusselt number divided by local Reynolds number multiplied by Prandtl number raised to 1 by 3 is equal to 0.332 divided by local Reynolds number raised to 1 by 2, which will be equal to CFX divided by 2. So this CFX is the local drag coefficient. Now this LHS we have to equate with the Stanton number, or we have to get from this particular LHS we have to get the relation with the Stanton number. So the LHS of the equality can be rewritten as the local Nusselt number divided by local Reynolds number multiplied by Prandtl number raised to 1 by 3 is equal to local Nusselt number divided by Reynolds number multiplied by Prandtl number multiplied by Prandtl number raised to 2 by 3 is equal to Stanton number, local Stanton number multiplied by Prandtl number raised to 2 by 3. Now this local Stanton number multiplied by Prandtl number raised to 2 by 3 is equal to CFX divided by 2. Now this equation is giving interrelationship between heat and momentum transfer. The above equation has been designated as a Colburn analogy. For Prandtl number is equal to 1, the Reynolds and Colburn analogies are the same. If you put up Prandtl number is equal to 1, we will get local Stanton number is equal to CFX divided by 2. Thank you.